Okay, I think we're on. So we are powering our way into spring break here. So we got this week and one assignment that's due on Wednesday. It's very short, but the problems are kind of lengthy. There's only 5 problems on there, but each one takes a little bit of work. But once you get the hang of it, it's not that bad. And then this assignment is due after spring break. And so I hope that the weather forecast is really bad for Wednesday. So I hope that that doesn't interfere with our Wednesday lecture so that we can be prepared for this homeworks. But in case that it does, I can always tape that lecture so that you can look at that over spring break and still be able to work on this homework, okay? 3.1, which is due after spring break. So that one's a little bit lengthier, but the individual problems are shorter than the ones in this homework. But I'm going to show you how to do those problems right now. And then I put in a extra credit assignment. So this is just an extra credit assignment, not due until after spring break. And then there's a quiz on these 2 homeworks, not due also until after spring break. So you'll have to finish both of those homeworks before you can work on that quiz. Okay. I think that extra credit assignment, forget what I put in there, but I think that extra credit assignment is things that were already on test number 1, so you could actually work on that one at any time. So you need an 85 there, okay, to get the credit for that. John's looking for the roll sheet. Balky's test. Is Christian here? Vanasco? Christian, okay. Those are the last 2 tests I wanted to return. Okay, so everyone has their test back. So what y'all were going to do for me for today is to make out this table to estimate this instantaneous rate of change for this particular function at the input 57. That is the that's what you're asked for here, and then interpret that value in the context of the problem. So this is that second problem in that activity 3 sheet, okay? So this is an applied problem. So remember now what this formula was supposed to indicate is the amount that men spend on underwear in a given year at a particular age, okay? So this is taken from real data. So we were joking last time that guys just don't spend that much on underwear, apparently. Okay, all right. But at any rate, that amount changes over time, as they get older, and so there's actually a graph of that function. Okay, there's a graph of that function. And we were trying to, or we're not trying to, we're going to estimate here to 3 decimal places the instantaneous rate of change at the input 57. So 57 is about right here. If you can see that better on your handout. So than the printout here on the screen. But 57 is about right there. So we're trying to estimate that instantaneous rate of change at 57, which is the same as the slope of that tangent line if you draw one there at 57, okay? So we could draw that tangent line on the graph and get an estimate, but last time we were showing how using this limiting process we could arrive at a much better estimate, much more accurate estimate for that instantaneous rate of change by drawing secant lines, right? From the input 57 over from 57 to the right a little bit, and by using progressively smaller increments, then we could ultimately there project what that slope of that tangent line is going to be from looking at the slopes of the secant lines. So by filling out this table, what you're doing is calculating a bunch of slopes of secant lines. But remember, those secant lines, as we make this increment progressively smaller, are going to look more and more like the tangent line. And then by looking at this pattern of these slopes of these secant lines, you can project what the slope of the what the correct slope of the tangent line must be. Okay, so that's the purpose of filling out one of these average rate of change tables. Okay, so if you're doing this strictly by hand, then this is going to be a little bit clumsy to fill out because it does have some calculations involved. But remember, we were going to use Desmos here, the computer, to help us do this work, right, without having to invest too much time in doing those calculations. So there's that average rate of change screen, okay, that we were using last time, and I gave you a link to that on your website homework page, and all you had to do was fill in the correct formula for that function f. So there's the correct formula filled in from that problem number 2. And then by changing the increment, right, well, you have to fill in the correct starting value, which for our problem is 57 because we're trying to estimate the instantaneous rate of change at the input 57. In other words, at age 57, okay? And then by filling in this increment, right, and changing that to progressively smaller and smaller values, right, you could ultimately then use the computer to calculate the slopes of these secant lines and then make your projection about what the slope of the tangent line must be, right? Okay, so I've already filled in this average rate of change with the first few values that you need, well, the values that you need for the first row in that table, okay? So, so let's fill in some of those things. Y'all have those written down? Okay, so A is 57, the F of A is 11.5913. That's not going to change because we're keeping the same A value each time. So F of A just means what I get when I plug 57 into my formula, right? Okay, so that, in other words, is the amount of money that a typical guy spends on underwear at age 57. So $11.59, all right? Not a lot, okay? The first increment in that table was 20. Okay, and so when you take A plus the 20, that brings you to 77. So that's where we're going to draw the secant line to, right? This is 57, and this is 77, right? So that's where we're drawing our first secant line, and there's the there's F of 77. If you plug 77 into the formula, you'll get 6.3073. So that's this output value here. And then there's the slope of that secant line is the last thing that we look at here. It's minus 0.2642. Okay. So if you haven't got that written down, let me fill it out here. In the chart. Okay. So F of A was what? 1159. Okay, 1159.13. Okay, and then A plus H was 77, right? Okay, because A is 57 and H is 20, so A plus H was 77, and then F of A plus H, what you get when you plug 77 into the formula is, we can do that by hand, but again, that just showed us it was what, 6 something? 6.30. Okay, so about 6.30. Okay, that's close enough. And but we don't really have to write these values down perfectly because what we're really interested in is the slope of the secant line. Okay, so that's where I want to write down some more decimal places. So what was that first slope of that secant line? Negative 0.26 what? 4.2? Okay, right. Okay. So when you draw that secant line, again, over from 57 over to 77, that's what the slope is, okay? And then, again, what we're going to do is let the increment be progressively smaller, right? So we'll be drawing secant lines that are that look more and more like the tangent line, until ultimately you really won't be able to tell the difference between the secant line and the tangent line, and then we'll be able to use that to project what the correct slope of the tangent line must be, and that's the instantaneous rate of change that we're looking for here. All right, so let's cut right here to the chase. So when you're filling out the table, you want to fill in those different increment values that are suggested in the table, but let's speed things up a little bit here, and let's go right to a fairly small increment. So let me go right to 0.1, okay? So I skipped over the 10 and the 5, or what those first couple of rows in the table, okay? And jumped right down to an increment of 0.1, okay? And when you have an increment of 0.1, right, already you see you can not even tell the difference between, this is a secant line that's drawn here, okay? It really does cross 2 points on that graph, but the 2 points are so close together that you can't even distinguish them. Okay, and so because we're drawing the secant line from 57 over to 57.1, so that's so close together in this graph that you can't distinguish those 2 points. And the slope of that secant line that I have drawn here is minus 0.13883. Okay, so let me fill that into the table in the 0.1 column there. So you'll have a couple other rows that you would have filled out, but 0.13883, okay? All right. And now let's go ahead and fill out the rest of these so we can, with these different smaller increments, right, so we can project what that, what the slope of that tangent line must be, okay? So if I go back here, let's change this to a 0.01, right, okay? And see, that's just... And visually, you can't tell any difference between this new secant line and the previous secant line, right? Okay, because you can't distinguish those points. But the slope did change a little bit, okay? So that is a slightly different secant line because the slope now is, instead of minus 0.1388 or whatever it was, now we're down to minus 0.138263. Can I remember that? Minus 138.263, okay? So see, the slope there did change a little bit, right? Okay, and now let's give it even smaller increment, and again you'll see the slope of that secant line changes a little bit, but not too much, right? Now it's minus 0.138206299, etc. right there. Okay, so already to 4 decimal places, what, minus 0.1382, was it 0 here? Yeah, 0. Okay, so already to 4 decimal places, notice that the slope of that secant line has stabilized now, right? Okay, to 4 decimal places, it's staying the same at minus 0.1382. The 5th decimal place changed a little bit, okay, but that's just a tiny little difference. And now let's plug in, just make one little small change there. Let's make that 0.001. And again, did it even change it at all? Yeah, I think it changed it slightly, but it was in the 5th or 6th decimal place. And again, the first 4 or 5 decimal places there already are now staying the same, right? So in the 5th row of that table, you could have put, again, minus 0.13820, okay? See, changing that increment from 0.001 down to 0.0001 didn't even change 5 decimal places of the slope of that secant line. So I think it's pretty obvious, right? At least to 3 decimal places, even to 4 decimal places, it's pretty obvious, right? What is the instantaneous rate of change? In other words, what is the correct slope of the tangent line? It's got to be what? Negative. Yeah, okay. Keep going there. All right. What? No, to 3 decimal places.
Yeah, we want 3 decimal places here, right? So minus 0.138, right?
Okay, to 3 decimal places, it's got to be minus 0.138, right? Because the 4th decimal place we can see is going to be 2, right? All right, and so when you round that to 3 decimal places, you're going to get minus 0.138.
Okay, so the correct instantaneous rate of change to 3 decimal places, everyone should have agreed, was minus 0.138. See, so we got it very accurate there, all the way to 3 decimal places, and everyone got the same value, so we don't have to worry about different people drawing different tangent lines and coming up with slightly different numbers. By the way, what does that tell us, by the way, about this particular situation? So how do we interpret that instantaneous rate of change in context, right? So you would say what? At x equals 58, I'm sorry, at x equals 57, or you could say at age 57, if you even want to be more precise there. So at age 57, what? So a typical man spends what? Well, about what? 13 cents or $0.138, right? Less on underwear, okay? What? And then we have to finish that off with, what's the last part that we have to put in here? This is a rate of change, so per year, right? Okay, per year. Don't say on. You don't have to say on average here, okay?
Because this is an instantaneous rate of change, right?
So you don't have to say on average from some age to some other age, okay?
All right? You would just say at this particular age,
Okay,
at exactly age 57. Okay, a typical guy spends this much less, right? It's less because it's negative, okay, on underwear
per year. Or you could have said the amount that a guy spends on underwear is decreasing by $0.138 per year, all right?
So this last phrase, you could have said that in slightly different ways, but the point is the amount is decreasing, right, each year by 0.138 at this particular age, okay? All right, so that's an awful lot of work, right? Okay, that's an awful lot of work to calculate an instantaneous rate of change, because you've got to fill out this table. So if I were asking you to, to calculate instantaneous rates of change at lots of different inputs for this particular function, you'd be filling out this table lots and lots of different times, and that's going to get a little bit tedious, right? Okay, so doing this lots and lots is going to be too slow, right, for to really be practical, all right? So what we need to do is talk about how to speed this process up, okay? By the way, this whole process now, remember, is referred to as calculating a limit or evaluating a limit, right? We're evaluating the limit of the slope of this secant line as the increment gets smaller and smaller. In other words, as the increment approaches 0. So you can summarize that whole table, that whole process that we just went through with this particular notation, right? You're finding what's the limiting value of the slopes of these secant lines as this increment gets closer and closer to 0. But remember, you can never let the increment be exactly 0, because if you let the increment be exactly 0, then this denominator turns out to be 0, and you'll end up dividing by 0 in that fraction, which you cannot do, okay? So you can't just jump down here and say, okay, I'll just let the increment be 0, then I'll know exactly the slope of the tangent line. That won't work because we can't divide by 0, okay? So we just make the increment smaller and smaller, and then sort of try to project, right, what's happening to the slopes of these secant lines as these secant lines look more and more like the tangent line. All right, but here's the trick.
there's no real reason to do this, to actually go through this process and actually numerically calculate all of these slopes of these tangent lines as you let the increment be smaller and smaller. You can actually do this because you're intelligent humans, right? You can actually visualize this process without actually having to do the calculations, all right? So that's what I'm going to show you today, okay? Here's the real secret to carrying out this limiting process, all right? Now, it does require a little bit of algebra. It does require a little bit of algebra, but fortunately, you don't know just a little bit of algebra. You know a lot of algebra, okay? So you have, by far, enough algebraic skills to do this, all right? Okay, so here's our example, and one example really, well, we really need two examples, okay? But once you've seen one example, you've really just about seen how this is done, okay? All right. So let's not use that. We'll maybe use that in a minute. Let's not use that example from problem 2 because it's got those, those ugly decimals in the formula. So let's take a little bit easier formula. Let's use f of x to be 4 minus 1/4 x squared. 4 minus 1/4 x squared. And let's see if we can use that limit definition. To calculate the instantaneous rate of change at the input 2, all right? But I'm going to do that without actually filling out a table. I'm just going to imagine what would happen if I filled out that table, okay? All right, now let me show you how we'll do this. By the way, here is that limit definition, okay? So I've got it written down formally here. And you do sort of have to memorize this limit definition because we're going to use it several times, okay? But you don't have to memorize all of this, everything that I have got written here, all right? But if you do have a function, any old function, it can be any function at all, that's smooth and continuous, so it's got to be smooth and continuous at a particular input, okay? Then, if you want to find the instantaneous rate of change at that input, okay, then you go through this limit process that we've just practiced now 3 times. Go through that limit process, and that's how you can calculate the instantaneous rate of change. All right. But again, I'm now going to carry out that limit process without actually having to do a lot of calculations in the table. Okay. I'm just going to imagine what the calculations would look like. All right. Let me show you how I can do that. So let's go back to the example. All right, so if I want to find f prime of 2, again, remember now, what the limit definition says is I need to find the limit, okay, as h approaches 0 of the slopes of a bunch of secant lines, okay? And those secant lines look like what? Well, they would be f of, what value am I starting at? 2, right? Plus my increment, right? Plus my increment. Minus f of 2, and what goes in the denominator now? It's 2 plus h, right, minus 2, all right? So remember, there's the point 2f of 2. That's one of the points on the graph, and the second point on the graph is 2 plus h, and then f of 2 plus h. So all you're calculating here is the slope of a secant line, okay? All right, now, so again, in the handouts, what we were doing was actually choosing values for h, right? So we were actually picking specific values for h, plugging them into this formula, and doing the calculations and see what values we get, okay? But in this example, I'm not actually going to choose a specific value for h. I'm going to carry out this arithmetic. I'm going to carry out all the arithmetic in this slope formula, but I'm not going to actually choose a value for h. All right? So I'm going to do a little bit of algebra here because I'm going to do a little bit of computations with this variable h. That's what algebra is. When you start doing calculations with variables instead of with real numbers, right? Okay? That's called doing algebra. All right? So let's see if we can do some of this algebra. Now, don't forget, at the end of this, we want to think about what's happening as h approaches 0, so do not drop this notation. Okay? If you drop this notation, you're going to forget at the end of this problem what it is you were trying to do at the beginning of the problem. Okay? So keep remembering to write this down. That is the number one mistake that students will make. They forget to keep writing this down over and over again. It sort of is just routine at first. You just have to keep writing it down because we're not actually going to be able to think about what happens as h approaches 0 until we actually carry out all of this arithmetic, all right? So at first you're just writing this down, writing it down, writing it down, writing it down. It's not until the last step that you actually get to apply that limit, okay? But you still have to keep writing it down. All right, now let's see. What would f of 2 plus h be? Okay, so what do you get when you take 2 plus h and plug it into this formula? All right, well, let's see. That's going to be 4 minus what? 1/4 times 2 plus h squared, right? Am I doing that right? Okay, yeah. I'm just going to take the 2 plus h and plug it in for x in the formula. Okay, and then you see we're going to have to grind through here a little bit of arithmetic. Okay, all right, so that's going to come up here in just a second, but let's not rush it. Okay, we'll get to that in just a second. Now let's do f of 2. Well, that's pretty easy, right? Okay, remember, put that in parentheses, though, because you're subtracting that entire quantity f of 2. So when you plug 2 in here, what do you get? You get 4 minus 1/4 times 2 squared, right? So I'm just going to plug 2 in for x into my formula. All of that is f of 2. So this is f of 2. Now, what about in the bottom? That's really super easy. What's 2 plus h minus 2 simplified to? Just what? Yeah, that just comes out to be h, right? Okay. So in the bottom there, you just get h. All right. So we've got this big expression in the numerator now that we have to simplify. So we just have to grit our teeth, and we have to do it. But now we've practiced simplifying expressions like this several times, so don't get panicked, all right? You can do it. So I have 4 minus 1/4 times, and what's 2 plus h squared? Well, that's not just 2 squared plus h squared, right? That means you have to take the 2 plus h and you have to multiply it by itself, right? So don't get lazy suddenly. I've cautioned y'all about this, at least 5 times, right? 2 plus h squared is not just 2 squared plus h squared. That means you have to take the 2 plus h and you have to multiply it by itself. Right? Now, what about inside parentheses? Well, that's just all numbers, so that can't be too bad. So that's going to be minus what? 4, and then let's see, how much is 2 squared? 4, but you're multiplying times 1/4, so you'll get what? 1, right, yeah, okay. So you have 1/4 times 4, but 1/4 times 4, that's easy. That's just 1. So you have 4 minus 1 here, okay. All of that divided by h. I hope I'm not going to run out of room on my page. Oh, no, I got plenty, all right. So I thought ahead. Now, notice here, I just keep writing down limit as h approaches 0. That's how you read that off of the page, by the way. Limit as h approaches 0, okay? So for a while, you're just going to keep writing that down while you're actually simplifying this big, ugly fraction, okay? Now let's multiply the 2 plus h times the 2 plus h. So that's not so bad. Let's see, 2 plus h times 2 plus h, that's going to be 2 times 2 is 4, and then 2 times h is 2h, right? And then h times 2 is another 2h, right? And then h times h is h squared, right? And then we're so that's the 2 plus h times the 2 plus h. And now we're subtracting off there, well, 4 minus 1 is 3, right? So I'm subtracting off 3 here at the end. Still dividing by h. So I have the limit as h approaches 0 of, now let's see, I have 4 minus 1/4 times, what's inside the parentheses here? 4 plus 2h is 4 h's, right? Like the, isn't that the club for farmers, 4-H? Is that 4-H? Is that what I'm thinking of? Do you know what I'm talking about? Okay. And now we can multiply through the 1/4. Okay? So we have 4 minus, well, what's 1/4 times 4? That's 1. 1/4 times 4h, that's easy. That's just h. Okay, oops, forgot to change the sign there. So there's another easy mistake to make. Make sure you distribute your sign properly, right? So minus 1/4 times 4 is minus 1. Minus 1/4 times 4h is minus h. Okay? And then we have minus 1/4 times h squared. Well, I don't think there's much I can do with that. That's just minus 1/4 h squared, right? Okay? And then minus 3. And then all of this divided by h. And now at this point, and this usually is what's going to happen, so if you've done your algebra correctly, at this point, a bunch of things will start to cancel. All right? So here I have 4 minus 1, right, which is 3. But then I have 3 minus 3, so guess what? All of the constants are going to disappear, okay? So you end up with no constants. So you have the limit as h approaches 0 of what is that? Minus h minus 1/4 h squared, all that divided by h. And the canceling just keeps going because notice h divides into both of these terms, right? See, h divides into both of these terms. So you end up here with canceling that h out of the denominator. That's really nice. So you have the limit as h approaches 0 of, what's left there? Minus h over h is what? Minus 1, is that right? Okay. And then minus, is it 1/4 times h? There we go, right. Minus 1/4 times h. All right. So see, that's, now that, you've simplified that fraction completely. Okay. All right. Whew. All right, see, that took a little bit of work, right, but we got there. It wasn't difficult work. It just took us a little while, right? Now you're in just the right spot. You've gotten right where you want to, because now you're going to think about, what's going to happen to this quantity? What happens to this quantity as h gets really, really small? So as h gets closer and closer to 0, what happens to minus 1 minus 1/4 h? Well, nothing happens to the minus 1, right? Because h is not involved in that first term. But what happens to minus 1/4 h as h gets really, really tiny? What is that quantity going to? As h goes to 0, this quantity is going to what? Is that where you're confused about, Keys? Right. Okay. You're looking a little... Okay, all right. So again, all right, let me ask the question again. As h gets really, really tiny, think about it. What is going to happen to minus 1/4 times h? It's going to get tiny also, that's right, yeah. As h gets closer and closer to 0, minus 1/4 times h is also going to get closer and closer to 0, right? If you start plugging in smaller and smaller values for h here, this second term is going to get really, really small. So ultimately, what are you going to get left with out of this expression as h gets closer to 0? You're just going to get left with what? What? Yeah, y'all are acting shy, but say it. What? Negative 1, that's right. All that will be left out of this quantity is minus 1, because this term will get very, very tiny, right? Okay? As h gets small, this part's going to get really, really small, and ultimately, all you'll be left with is minus 1. There's the answer, okay? That's it, all right? As h gets really, really small, okay, this quantity is going to get really close to minus 1. Ah, we got it, okay? Now, we did have to do a little bit of work, but we didn't do that many computations, right? Okay? So there, finally, look at what we were trying to find. There is my value for the instantaneous rate of change at 2, okay? There I come up with minus 1, all right? Got to be minus 1. By the way, we did that before with this same function, but we did it by drawing the tangent line, and what did we come up with? We got a very good estimate by drawing the tangent line. We got minus 1, right? Okay. All right. Well, here I did it without having to draw the tangent line, without having to look at the graph, or without having to draw the tangent line. There it is. Okay.
that the slope of that tangent line has to be, at the input 2, the slope of that tangent line has to be
minus 1. Just got to be, right? Okay. Ooh, neat. Okay. So now that took a little bit of algebra, but we didn't have to fill out that table. Okay. So we didn't have to do any calculations. And, well, we had to do a few calculations, but the only calculations we did were calculations we could do by hand. We certainly didn't have to rely on the computer. Okay. We did not have to rely on the computer at all. So this we did without having to use the computer at all. All right? Are we going to have to try that one again? Okay, let's try another one. So we'll use that same formula, okay? Let's try another one. Let's just pick a different input. So y'all pick an input for me where you want to find the instantaneous rate of change. So let's use the same function, 4 minus 1/4 x squared. There's the graph of it, by the way. So y'all pick an input for me where you want to find the rate of change. What? 10, way over here? Yeah, try something in the graph here that's maybe a little bit friendlier to me. Okay. Let's try, for fun here, let's try 0. Okay. So let's try finding the instantaneous rate of change at the input 0. By the way now, Zena, what would you expect that to turn out to be? 0. Yeah, right. Why 0? Because if you draw the tangent line right there, what side of the line are you going to get at the input 0? There's the input 0. Yeah, you're going to get a horizontal tangent line, right? And horizontal lines have slope 0. So we're expecting to get a result there of 0, okay, just from looking at the graph. If you pick something over here on the left, you're going to expect that slope to turn out to be what? Positive, yeah, because all of these inputs over here on the left have to have positive slope, right? Okay. All right, well, let's try 0 and see what happens. So let me scroll down here here's a blank page. All right. Okay. So again, what we're trying to find here is f prime of 0, right? Which I'm thinking from looking at the graph is going to turn out, f prime of 0 is also going to turn out to be 0. Okay. Right? But imagine that I didn't see the graph. I'm just trying to calculate f prime of 0. How would I arrive at that fact that it's going to come out to be 0? Okay. Well, remember, you use this limit definition. So you take the limit as h approaches 0 of f of, okay, what goes in here now? So what's the first thing? 0 what? Plus h, right? Okay. Minus f of 0, all right, over 0 plus h minus 0. By the way, in all of these problems, the denominator always turns out to be h, okay? The denominator always simplifies to h. The numerator, though, could be something completely different, all right, depending on what the actual function formula is, all right? So we want the limit as h goes to 0 of, all right, let's see, what's f of 0 plus h? That's 4 minus 1/4 times 0 plus h squared. That was the formula for f, was 4 minus 1/4 x squared. So when you plug 0 in, this is what you'll get. Remember, f of x was 4 minus 1/4 x squared. So when you plug 0 plus h into this formula, that's what you get. Minus the f of 0. So let's see, what's f of 0? That's 4 minus 1/4 times 0 squared. All right. Now I'm just plugging 0 into the formula. All of that divided by h. Okay, so this now is going to simplify much more rapidly than the previous example, because what is 0 plus h, of course? That's just h. So all you really have here is h squared times 1/4. So you have 4 minus 1/4 times h squared. Well, Well, that's so easy, see? Okay. And then here, this is just going to be, well, 1/4 times 0 squared is 0, right? So you end up really with inside the parentheses just minus 4. Oh, gosh, so nice, right? Because what happens to the 4s? They cancel. So you have 1/4 times h squared, minus, right? Minus 1/4 times h squared, and then all of that divided by h, because the 4, this is 4 minus 4, so that goes to 0. And now what happens to your h in the denominator? It's going to cancel out with the h squared. So you end up here with the limit as h approaches 0 of minus 1/4 times h. That's it. And now you just have to apply your imagination. Okay? So your intuition. It's going to work perfectly every time. As h goes to 0, what happens to minus 1/4 times h? It gets very, very small, right? Because you're multiplying minus 1/4 times a smaller and smaller and smaller number, you see, as h goes to 0. So eventually it's just going to disappear, right? Okay? And so you can imagine now that this limit just turns out to be what? No, not negative 1/4, because the minus 1/4 is multiplying times h, but h is going to 0. So you see you're multiplying minus 1/4 times a smaller and smaller and smaller number. So what do you end up with there? 0. Yeah, that's the correct answer, right? Okay. That minus 1/4 times h also has to be going to 0 if h is going to 0. So there it is. So see, now the limit is gone because we've imagined what that limiting value is, and there's our answer. F prime of 0 is indeed 0. So we've confirmed what we thought, right? The slope of the tangent line is 0. Okay? All right, now let's try one that we just did. All right? So we were just looking at that underwear formula, okay? And what was that underwear formula? It was minus 0.0063 times x squared, is that right? Plus was it plus? 0.58 times x, and then minus 1, okay? You're going to find out that minus 1 makes very little difference at all in the calculating the rate of change, all right? Okay? But it is part of the formula, all right? And what we estimated was f prime, the rate of change at the input 57, okay? All right. This is as hard as they get, okay? And so let's try this one. So we already figured out, we already estimated before that this is going to come out to be what? I could write approximately, but might as well write equal. So what did we get from our table? Minus point what? 138. Okay. So let's see now if we can duplicate that by hand without having to use the table. Okay? All right, so could we have done this now without having the calculator? All right? Well, we're going to have a calculator here because we've got some decimals in the problem, but without using that average rate of change table. All right? So, table builder. So, again, how do we do this? You're going to take the limit as h approaches 0 of what? F of 57 plus h, right? Minus f of 57, okay? All of that divided by 57 plus h minus 57, all right? Oi, okay? All right, so f of 57 plus h. Okay, so this is going to be a little bit ugly, but now don't get intimidated, all right? Okay, because you can do this. So it's going to be minus 0.0063 times what? 57 plus h squared, right? Plus 0.58 times 57 plus h. And then don't forget the minus 1. Okay. Let me move all this over a little bit so I've got plenty of room here. Right? And then we're going to subtract off the f of 57. So what's f of 57? That's minus 0.0063 times 57 squared plus 0.58 times 57, and then minus 1. Ooh, I could barely fit that in there. All right. Can y'all see that? Did I do that right? So minus 0.0063 times 57 squared plus 0.58 times the 57, and then the minus 1. Remember, you're subtracting off all of that because all of that is f of 57. Okay? So we are going to have some decimals there, okay? But be patient because in the long run, a lot of things are going to cancel, all right? Y'all see where I got everything now? So minus 0.0063 57 plus h squared. I just plugged the 57 plus h in for x. And then here's the 57 plus h plugged into the second term, right? So you got 0.58 times that. And then there's the minus 1, minus, and then all of this in parentheses is f of 57. Minus 0.0063 times 57 squared plus 0.58 times 57 minus 1. What's in the bottom now? I can do that. So I'll do half of it. I'll do the bottom part, and I'll do the top part. Is that fair? Okay. All right, so what's in the bottom? H, right. So the bottom just simplifies to H. So, see, at this point, everyone gets a little bit depressed because they're thinking, wow, this is a lot of arithmetic, okay? And it is a little bit of arithmetic, all right? But I promise you, in the long run, it'll work out just really nicely, all right? Okay, all right, so let's take the 57 plus h, and now we have to square that, of course. Don't forget you're multiplying it by the 0.63, right? So what's 57 plus h squared? That's just 57 plus h times 57 plus h, right? What's this going to be now? All right, so now you need your calculator. So what's 0.58 times 57? What now? 33.06. Okay, and then plus 0.58 times h. So that's not bad because you're not really doing any arithmetic there. 0.58 times h, right? And then don't forget the minus 1. You don't want to forget the minus 1. Okay. And now what's inside the parentheses? Okay. So now y'all have to help me with this. So minus 0.0063 times 57 squared. Okay. So how much is that? It's going to be negative. Negative 20 point what? 4687. All right. I know what 0.58 times 57 is because y'all told me that. That's 33.06, right? And then we have the minus 1 thrown in here. Okay. So I had the minus 0.0063 times 57 squared. And then the plus 0.58 times 57. That was 33.06. And then the, don't forget the minus 1 that's on there at the end. Okay. Now, let me point out something to you why things are already looking bright, although you've got a lot of numbers written down there. Notice here you have 33.06, right? But notice over here you also have the 33.06, but you're going to have a minus in front of it, right? Because it's inside the parentheses. So guess what? Those things are going to cancel each other ultimately, right? So all that's going to come out to be 0. So it looks terrible, but that's just going to come out to be 0. Notice here you have a minus 1, but this is going to end up being a plus 1 because you have minus a minus 1. So that 1 and that 1 are also going to cancel. Okay? So my point here is it looks a little bit gruesome right now, but in the long run, a bunch of things are going to cancel here. Okay? So if you're patient, right, and stick with it, and are careful about your algebra, a bunch of things will cancel, okay? And in the end, you won't have such a bad expression after all right? Well, we have to get to that point, though, so let's go ahead now and try to multiply 57h plus h times 57 plus h, okay? All right, the only hard part there is 57 times 57. How much is 57 times 57? What now? 3249, okay? And then you have 57 times h. Well, that's easy. That's 57h. And then you have h times 57 again. So that's another 57 times h. And then you have h times h, which is h squared, okay? And now let's copy down some of this other stuff that's sort of just going along here for the ride for a moment. By the way, if you wanted to at this point, you could go ahead and take the minus 20.4687, add it to the 33.06, and subtract off the 1. So you could simplify all of those numbers inside the parentheses just to a single value. But I'm going to leave them just not added together yet, okay? So if you want to, you can add them together. Do it carefully, though. But if you don't want to add them together, you really don't have to at this point. I'll show you why here. It's because what I mentioned a moment ago, a bunch of things are getting ready to cancel on us. All right? All right, now, let's distribute that minus 0.0063. Okay? So what is minus 0.0063 times 3249? Well, I can tell you right now, it's going to turn out to be minus 20.4687. Is that right? Yeah, because we've actually already done that, okay? That is minus 0.0063 times 57 squared. That's exactly what this number was, all right? And then you have minus 0.0063 times 57h. So how much is that? And then multiply by the minus 0.0063 gives you what? 7 point what? 0.7182. So Zena was trying to hurry me along there. She said 57h plus 57h is 114h, right? Okay. And then she multiplied by the minus 0.0063, and that turned out to be minus 0.7182 times h, don't forget. Okay, so minus 0.7182 times h, and then you have the minus 0.0063 times h squared. Okay, the minus 0.0063 times h squared. All right, so down to that, and now let's keep all these other values. So plus 33.06. And then plus 0.58 times h, and then minus 1. And now I'm going to distribute that minus sign through the parentheses here. So I get plus 20.4687 minus 33.06, and then plus 1. Finally, at the end, plus 1. So don't forget to distribute this minus sign now, so all the signs inside the parentheses will change. Okay, so that negative 20 becomes a plus 20, that plus 33 becomes a minus 33, that minus 1 becomes a plus 1. Now, what cancels out at this point? Well, I hope a bunch of things cancel out. There I have a minus 20.4687, and there I have a plus 20.4687. So guess what? That is going away. So this one and this one disappear. What else cancels? There's the plus 33.06, and there's a minus 33.06. So that's gone away. And then I have a minus 1 and a plus 1, right? So those two things are going to cancel each other. So see, it looks like I had a bunch of ugly terms there, but not so bad. So I have minus 0.7182 times h, right? And then minus 0.0063 times h squared, and then plus another 0.58 times h. Is that everything? This, and this is all that's left, right? All of that divided by h. Now, guess what? Okay, look what's going to happen. All of these terms have h left in them, right? All of those terms have h left in them. So you can divide out the h in the denominator. The h in the denominator is going to go completely away, right? So you get the limit as h approaches 0 of minus 0.7182. See, that h divides out. And then minus 0.0063 times h, because h squared divided by h just leaves you with an h. And then what happens here? The h goes away again. Okay? So now we're down to this. All right. So that was a little bit of algebra, but we're right exactly where we want to be, because now we can apply the limit. What now? Yeah, that's what I'm getting ready to do. Because now what's going to happen when h goes to 0 here? Does anything happen to this term? That term doesn't have h in it, right? Okay, so when h goes to 0, it doesn't really matter at all, right? That term stays minus 7182. What happens to this term, though? That's what's important. As h goes to 0, what's happening to this quantity? It's getting very, very small, right? So eventually, as h gets really tiny, this term is going to disappear. So that term just sort of disappears. And what happens to this term? Doesn't change at all, right? Doesn't matter how big h is, right? Because there's no h involved in that term, you see. So ultimately, when h goes to 0, all you get left with is the minus 0.7182 plus the 0.58. That's it, because the middle term will disappear. And what is minus 0.7182 plus 0.58? I left off the point there. Isn't it 0.1382? Yeah, okay. It's 0.1382. There it is. All right. Remember what we were looking for? Forgotten already? That is the instantaneous rate of change at 57. There it is. Okay. Done without the computer. We needed a calculator, right? But we didn't, because we had some decimals that we had to calculate. But we did it without the computer. Now, what did we get on our sheet when we did this? I think we got minus 0.1382, didn't we? Yeah, okay. But there we got the same value, you see, by hand, essentially by hand. So the instantaneous rate of change at 57 is minus 0.1382. Okay? Because we can,
because we're very intelligent beings, right? See, we can imagine what happens as the increment is getting closer to 0
without actually having to plug in small values for the increment, you see. Okay? Our intuition can tell us what's going to happen when the increment gets small. We don't actually have to plug in small values for the increment and see what happens. All right? So I'm fairly convinced that is the correct instantaneous rate of change. All right, now, that's a lot of work, right? Still a lot of work, right? And prone to mistakes, right? Because there's some algebra involved, okay?
So if you had to calculate a bunch of instantaneous rates of change for this formula, right? If you had to calculate, f prime of 30 and f prime of 40 and f prime of 50, in addition to the f prime of 57, you would get exhausted, right?
Because that's a lot of calculation still to calculate one instantaneous rate of change. But again, this is where we can take advantage of algebra. Actually, what we can do is find a formula that will give us the instantaneous rate of change, okay, for any input, all right? So we don't have to go through this process over and over and over again to calculate instantaneous rates of change. What we can really do is just go through this process once, okay, and find a formula that will output for us always what the correct instantaneous rate of change is for different inputs. That's what I'm going to show you now, okay? So if you're thinking, gee, every time I have to calculate an instantaneous rate of change, I have to go through that limit process, the answer is no, you don't, okay? You just have to do it once for a particular function, just once for a particular function, and then you can use that knowledge over and over again to calculate instantaneous rates of change for new inputs, all right? So that is what I'm going to show you now, okay? It's actually exactly the same process, all right? Exactly the same process. All right, so suppose we had a function called f, and its formula is x squared plus 2x, x squared plus 2x, all right? And I want to be able to calculate f prime, the instantaneous rate of change, at a bunch of different inputs for this function, all right? So not just one input. I just don't want to calculate f prime of 1 or f prime of 2 or f prime of 3, but I want to be able to calculate a bunch of instantaneous rates of change for this particular function, all right? Then here's how I can do that efficiently. So I'm going to calculate the instantaneous rate of change not at a particular input, but I'm going to use a variable here, okay? So I'm going to not plug a particular number in for x, but I'm just going to use the variable x. So again, we're applying our knowledge of algebra here, all right? So let's calculate the instantaneous rate of change at the number x, but I'm not going to pick a specific value for x, all right? I'm going to keep x as a variable. Right, so how would that look like? Again, this is not f of x now. This is f prime of x, right? So be careful. F of x is x squared plus 2x. But what I want to know is, what is f prime of x, right? So let's apply now our limit definition again. So we would take the limit as h goes to 0 of f of what? X plus h, that's right. Do not pick a specific value for x. Just keep x as a variable. All right? Minus f of what? X. Minus f of x. All of that divided by x plus h minus x. Yeah, I do know it's going to cancel out, so I could just write h. You're right. Okay. I just like to keep re-emphasizing that what we're finding here is a slope. Okay. Yeah. All right. So it is immediately going to cancel to h. But see, the trick here now is I'm going to try to evaluate this expression without plugging in a specific value for x. So before, we were picking specific values for x and evaluating this expression. All right. Now I'm not going to pick a specific value for x. I'm going to try to do all of this algebraically without picking a value for x and without also picking a value for h. Okay. So I'm going to try to do this all abstractly without choosing numbers for x or h. And you can do that because you guys know how to do algebra, you see. Okay. That's what algebra teaches us, how to do this arithmetic without picking specific values for the variables. That's the power of algebra. All right, so what is f of x plus h? What's my formula for f? It's x squared plus 2x, right? So f of x plus h would be what? X plus h squared, isn't that right? Plus 2 times x plus h. All right, that is f of x plus h. That's what you get when you plug x plus h into this formula. Minus f of x. Be sure to put this in parentheses now. This is a common mistake. So you're subtracting off the entire quantity f of x. But of course, what is f of x? That's so easy. I know what f of x is, right? That's x squared plus 2x, right? If you plug x into this formula, well, you're going to get the same thing, right? So that's just x squared plus 2x. And then, all right, Zena, tell me now, what's the denominator? H, yeah, right, okay, right. Okay, so that's the easy part. But actually now the top part is not hard either. It's actually easier to do it this way than plugging in a specific number for x, because now you don't really have to do any arithmetic. Well, you have to do a little tiny bit of arithmetic, but you don't have to do very much arithmetic at all, you see, okay? So you really don't need a calculator here even. X plus h squared means x plus h times x plus h. So please don't make that mistake. All right? Don't write down x plus h squared as x squared plus h squared, right? You have to multiply it by itself. And then what's 2 times x plus h? That's easy. That's 2x plus 2h, right? Minus x squared minus 2x. Why minus x squared minus 2x? Because I'm distributing the minus sign, right? The x squared plus 2x is in parentheses, so I have to apply that minus sign to both terms here. All of that divided by h. So don't forget now, keep writing down limit as h goes to 0. I know it gets a little bit tedious to keep writing that down, but you have to keep writing that down because you got to remember what you're going to do at the end here. So let's see, what's x plus h times x plus h? Well, x times x is x squared, and then you have x times h, so that's hx, and then you have h times x again, so that's hx, and then you have h times h is h squared, and don't forget you've got the 2x and the 2h, and then you're subtracting off x squared, and then you're subtracting off 2x. And if you've done this right, a bunch of things in the numerator now are going to disappear. So if you've done it wrong, you know you should start having this sinking feeling, because if you've done it wrong, a bunch of things in the numerator will not disappear. And that's always a signal that you need to go back and check your work again. But in this case, do we get a bunch of things disappearing? I think so, right? Because here we have x squared, and here I have minus x squared. What a relief. So those go away. Here I have plus 2x, and here I have minus 2x. So the 2x goes away, right? So what are you left with here? Just the limit as h goes to 0 of what? 2hx plus h squared plus 2h, is that right? All of that divided by h. So that still looks kind of gruesome, except it's not, because h divides into all of these terms. So there's the next thing that should happen. If you've done this correct, you should be able to cancel the h out of the denominator. So if you can't cancel the h out of the denominator, I almost can guarantee you something has gone wrong. But h goes into all of these terms, So you can reduce that h, and you get the limit as h goes to 0 of what? Well, 2x plus h plus 2, is that right? Yeah, okay. And what happens to that expression as h gets really small? What will be left in that expression? Just not 2x plus h, but 2x plus what? 2. Yeah, this term is going to disappear, right? See, as h goes to 0, that middle term becomes meaningless, right? Okay. In the parlance of calculus, we would say that middle term becomes infinitesimally small, and all we're left with here is 2x plus 2. Ah, there it is. 2x plus 2. Now you're wondering, there it is. What are you talking about? There it is. What is there? Okay? That's it. What that formula is telling you is this. For any input whatsoever to this function, for any input, if you want to find its rate of change, wow, what a relief. If you want to find its rate of change, just take the x, multiply it by 2, and add 2 to it. Okay? That's what that's telling you. So you can immediately now calculate rates of change just like so fast. So what's f prime of 4? 10. Yeah, that's it. Ah, what's f prime of minus 1? 0. Yeah. What's f prime of 3? 8. Exactly. Okay. See, now you've done it once, and one size fits all there. Okay. For any input for this particular function, for any input, you can find its rate of change just by multiplying the input by 2 and then adding 2 to it. Okay? So you can calculate every single possible rate of change for this function, x squared plus 2x, by using this formula. That is called the derivative function. That's called the derivative function, or the rate of change function. The rate of change function tells you what is the rate of change at any input, and you don't have to go through this limit process now for that function ever again. Okay? All you have to use is the 2x plus 2. Oh, by the way, this is interesting now. Okay? So what does that tell me, by the way? The fact that f prime of minus 1 is 0, I know something now that I didn't know before. What's happening at minus 1 for this function? Well, the function isn't constant, but there is something interesting happening at minus 1. What is the rate of change at minus 1? 0. That means the slope of the tangent line is what? 0. Ah, so that tells me at minus 1, I have to have a turning point, right? Okay? At minus 1, there must be a turning point. So I don't know what the graph of this function looks like, okay, because I didn't graph it. But at minus 1, there must be a turning point. Because I don't know if it's a peak turning point or a valley turning point, but at minus 1, there's a turning point because that is where the tangent line has slope 0. At 4, on the other hand, the curve is increasing, right? Because this is positive. At 3, also the curve is increasing because the rate of change is positive. All right? Okay, so there's the trick. All right? If you want to find, for any function, if you want to find a formula that will give you the rate of change at any input, you have to evaluate this limit. Okay? Do not pick a specific value for x. Do not pick a specific value for h. Right? Just grind through this limit using algebra, and you will get a formula. Okay? A formula that doesn't have h in it, by the way. The h has to disappear. And you can use that formula to calculate the rate of change at any input. Okay? Wow, y'all think y'all can do that? Y'all very confident. Okay? I hate to say I'm less confident, but I'm less confident. All right. This is exactly now what is in, if this will open for me. So this is exactly now what you're going to be doing in your homework 2.3. Well, it won't open. And it's trying to open. So you have several problems now, 5 actually, where you're going to be using this limit process to either calculate a rate of change or find the derivative function. All right? So be sure you read the instructions carefully. By the way, sometimes now, I forgot to mention it, the increment h is sometimes, let me go back to the notes here for a moment. Sometimes in the homework, the increment h is labeled as delta x. That's the Greek letter delta. So if you see delta x, that means the same as h in my notes. All right? Okay? So don't get confused by that. That just means the increment. All right, well, we're out of time, so give it a shot, and we'll look at it on Wednesday. Yeah, I do need, well, we'll collect it next time. So keep your homework till next time. We'll collect it next time. Which one? Well, that's in the notes, so you can get it from the notes. Okay. All right, okay.